Our last question is this idea of comparing growth rates. Now this actually works out to be a great lab, something to just sort of play with. But if we have some functions and we take the ratio of them, so here we have f of x and g of x, if we compare these two, the ratio of them, it actually tells us how fast they grow. If the limit is a constant, then it actually tells us that they grow at the same rate. However, if the numerator, or if the limit is infinity, then that means the numerator function is growing much faster. If the limit's 0, then that means this one is going to 0, or is going to infinity. So if the limit overall is 0, that means the g of x function, the denominator, is growing much faster. So we're going to do this right here and compare these two. So let's go. Limit as x approaches infinity. Okay, of f of x over g of x. So x squared over e to the x. Now hopefully in the back of your mind you're thinking, of course, e to the x grows much faster. It's an exponential function after all. But let's go ahead and explore. So using L'Hopital's rule there, we get the limit of 2x over e to the x. We can still apply L'Hopital's rule. It's still going to infinity over infinity, so that would be the limit of 2 over e to the x, which quite obviously goes to 0. Therefore, e to the x, I don't even need to say the word much there, but e to the x grows faster than x squared, which we sort of know, but we can prove that using calculus. All right, now let's compare the two functions, natural log of x and x squared. Okay, natural log of x over x squared. These are both going to infinity. Okay, we know they're getting larger as we go, so let's apply L'Hopital's rule. That'll be 1 over x over 2x, which algebraically that is equivalent to 1 over 2x squared, which equals 0. This shows us that x squared grows faster than natural log of x, which is not quite as obvious, but if you could convince yourself very easily by looking at their graphs over a short period of time.